sometimes take a day or so to get it up there because Canvas has to process it, or Integrity has to process it first. And the shorter it is, the faster they process it, but when you do the whole hour or more, it takes a while. Okay, so it was a week ago was the last time we had lecture, so you'll have to remind me exactly where we left off. So did we talk about bonding at all? Okay. What was that? It would be the response that you're looking for to change. So if you were testing a drug for blood pressure, it would be the blood pressure that you would be looking for to change. Okay. So with the electron distributions in there, your chemical behavior is going to be determined by the electron distribution. And see if I can get this to a size that's nice on the screen. Okay, that has everything up there. So those outer electrons, the valence electrons, when we look at that electron orbital model here, where you've got your nucleus in the middle and these shells around the outside, the first shell likes to have 2 electrons, second shell likes to have 8 electrons, the third shell likes to have 8 electrons. This model is usually not used for anything that is larger than this. And this is really all the larger we need to go for things that we study in anatomy and physiology. This is the simplest model to use, so that's why we're going to leave it at that in there. So how many electrons are in this outermost shell in there are going to determine a lot of the behaviors in there. So if it's got a full valence, if this shell has 8 in there and that's what it holds, it's going to be really happy. It doesn't need to react with anything to be happy in there. Likewise, if it's completely empty and this shell below it has 8, that's happy as well. But if it's only got a couple in there, or it's only missing a couple, it's really close to being at a happy state, and it's going to be more reactive in there. So this is looking at a 2-dimensional model in there. There is a 3-dimensional model that uses more of the dumbbell shapes and puts them in your X, Y, and Z axis, like this, that you've probably seen that in math. We're not going to get into that model in here. We don't really need that model to explain the behaviors we're looking at. So as you move out towards the sides of the periodic table here, what this one is going to show you here is this would be your far left side of the periodic table. In there, all of those are going to have 1 electron in their outermost shell. So when they only have 1 electron there, they're not even close to getting it filled. So that 1 electron is going to be by itself, and they're going to be pretty eager to get rid of it. They're so eager to get rid of it that you're not going to find anything in that state in nature. The only way you'd find any of these elements actually having that last electron is in a lab, stored in environments. A lot of times they'll store them under kerosene or something else because they'll react explosively with the air. So they're extremely reactive that way. The next row in, these have 2 electrons in that outermost shell. Again, it's not really even close to being full in there, and so they will also be very reactive. Again, not occurring in nature in there. Not quite as explosive as the first group, but still very reactive, too reactive to occur naturally. Too reactive to occur naturally. Over here, this would represent the right side of the periodic table. So over here, these are what they call your noble gases or inert gases here. These all have their outer ring full. They're happy. They don't want to interact with anybody. They're just fine by themselves. Over here, these are missing 1 electron. So they're going to be very reactive. They're going to be very aggressive at seeking that 1 electron. So fluorine is the one that is the most electronegative. It's going to want 1 electron more than any other element out there. So the closer you are to fluorine, the more aggressive you seek getting that electron that you need in there. So chlorine is right below it here. So can anybody think of something we use chlorine for? Pool. So you put it in the pool because you're hoping that it's going to kill the nasty little accident that somebody else had in the pool before you. And if you don't think that occurs, I swim all the time, and it's real regular that they close a pool and take out the chunks from either end. So what the chlorine is going to do is it's going to be very aggressive at seeking that 1 electron. So what it will do is it will take that electron from that nasty little bacteria that's floating around in the pool. When it takes the electron from it, it's going to alter the chemical makeup of that bacteria in there and kill it so that it can't harm you. So yes, the chlorine can be reactive towards your cells on your skin, but the idea is with a bacteria, if you lose 1 or 2 cells on your skin and they die, no big deal. Everything that's on the outer layer of you is dead anyway. However, for the bacteria, they got 1 cell. They are just the Lone Ranger out there, and if you kill their only cell, they're dead in there. So it's an effective way to try and help reduce your chances of getting sick from going into a pool in there. So what else would you use chlorine in? Bleach. And so that's what makes it so reactive as bleach. That's why it works as a disinfectant in there. So if we've had the microbiology lab in here the night before, or if they've been dissecting stuff out here on the counters, a lot of times when we come in here in the morning, it may smell like bleach because that's what we bought to clean the counters with in here. So over here, these are missing 2. They're going to be reactive as well, but again, not as strong as these. So these are closer to having the 1 electron. They're going to be more aggressive about seeking it. These need 2, not quite as aggressive about seeking it. These need 3, even less aggressive about seeking it. And then you've got carbon here in the center that's got 4 in silicon, and they will not generally do any type of bonding that requires giving up or accepting any electrons because they're riding on the fence. They're much happier to share. So this has a picture here. This is showing your 2-dimensional. This is showing the 3-dimensional with your X, Y, and Z axis. And then when you superimpose the models in there. So when we look at chemical bonds in there, the chemical bonds or the interactions between these electrons are going to be what is going to hold the atoms together. And there's a few different ways that this can happen. The covalent bond is going to involve sharing electrons. So with this one, you've got these clouds represented here that represent the hydrogen. And so remember, more yellow means that's where you're more likely to find the electrons in there. As it gets lighter, you're moving away from where the electrons are likely to be hanging out. If we use the Orbitals model, hydrogen has 1 electron in there. It wants to have 2 in that first shell. So what happens is it's really on the fence there. It could take it, it could leave it. It can do ionic bonding in there that we'll talk about in a minute, but where it is in there, it can also share. So when these get close enough together, we're going to have those electrons shared. They're in an overlapping circle. So now each hydrogen does have access to 2 in its little sphere of area that has electrons in it. Neither one has given up or lost them, but they have access to the other ones if they need it. So one way that they will try and go through and predict some of these shapes is to use these things called Lewis dot structures. In there, the Lewis dot structure, you look at how many electrons are in that outermost ring, and then you put these little dots around the chemical symbol for it. We don't really need to use them in here. It's covered in there as kind of an idea that this is one way that you can represent a chemical formula. So when we talk about there being 2 hydrogens, if you use the electron distribution diagram, it's that orbital model that shows them together. If you use the Lewis dot structures, it would be saying you've got 2 hydrogens next to each other like that to give you an idea of the shape. And then if you do the space filling model where it's more of those clouds, it shows the picture like this. And so if you have a double bond, what it means is it's going to share electrons with the neighbor twice. If you have a triple bond, it shares electrons with the neighbor 3 times in there. So the valence is that bonding capacity, or how many are in that outermost shell. The electronegativity, that is basically how bad it wants to bind with somebody. How strong is its pull for another electron in there. Most electronegative is fluoride. When you look at a periodic table, the closer it is to fluoride, the more electronegative it is. You're not going to have to figure that out in here, but it will come back for you in chemistry at some point. Chemistry can be a little bit nicer if you can take some of the chemistry you learn from biology. That's just my advice on the thing. So this is the covalent bond where they are sharing electrons. So another one that commonly does covalent bonding is carbon. So you've got 2 in that first ring, 4 electrons in that second ring. So it will bring 4 hydrogens in that each bring an electron. So now it can have access to 8 if it shares them with the hydrogen. So carbon does a lot of that bonding. There's a whole branch of chemistry that looks at carbon and hydrogen bonding like this, that you can take a whole year of that. What fun, huh? So with the nonpolar covalent bond, this is when they share electrons, but they don't necessarily share them equally. So if we look at oxygen here, 2 in the first ring, and it's going to have 6 in the second ring. So that leaves 2 empty spaces. So when hydrogen comes along, it can have a couple hydrogens come in and share electrons in there to fill things in. However, there is a significant difference in the electronegativity of oxygen and hydrogen in there. You can think of oxygen being like the big brother and the hydrogen being like the little brother. So if you have a big brother and a little brother and you stick them in the back of a car and you put some toys back there and you say, share them. Yeah, it doesn't always go that well. So the big brother's got these toys that he's accumulated over the years, all these electrons that he's going to keep on his side of the car. And those are his. He does not need to share. He wasn't told he had to share those toys. They were around before little brother was even thought of. So with these electrons over here that it doesn't have to share, it's going to have a partial negative charge just from them hanging out over in this area, so many negatives that it will create a partial negative charge over here. This little symbol just indicates a partial charge. The toys that it says to share, so if you have kids and you say, okay, here guys, share this. What happens when the one kid says, well, you know, I'm taking it all the way onto my lap? The other kid's going to squeal. No, don't do that. Sharing to them means you put that in the back of the car, it stays in the middle of the line in there. You don't get to haul it over there. And that's how these electrons are here. It's going to say to the hydrogen, yeah, we're sharing these, but leave them in the middle. You don't get to take them over to your side. So there's never any electrons that come and hang out over here. What you end up with is a partial positive. And it does it with both of them in there. So because you've created these partial positives and partial negative charges in there, what can happen is when you have additional partial positives and negatives that come along, the partial positive and negative charges will bond to each other in there. So this would be an example of nonpolar. Everything is equally shared. This would be an example of polar covalent. It's still sharing, but there's separate poles where things are not equally shared in there. And so that allows you to create these hydrogen bonds. So this here is water, and that explains a lot of the properties that go with water. So if you take a glass of water and you fill it up and you get it all the way full and you just keep on going, you'll notice it'll make the little bubble over the top. This is what allows you to have that bubble over the top, is the hydrogen bonds that want to hold all of those water molecules together. So does that make sense in there? Difference between polar covalent and nonpolar covalent? So then we have the ionic bond in here. And with the ionic bond, we have ions where your atom has become charged. It's a cation when it's positively charged, and anion when it's negatively charged in there. And so we're looking at over there on the far left, you've got sodium on there, and there's an electron in red in there. That's that one that it's not going to have in nature because it's too reactive. It's going to give that one up. When it gives it up, what happens is now it's got more protons than electrons, and so it will have a positive charge. Chlorine's real happy to take up those spare electrons in there. So you can see where that red electron has gone into the chlorine. Now it's got more electrons than protons, and it has a negative charge in it. So now we've got these positive and negative charged ions, and you've got positive and negative charges in there, just like you have positive and negative ends of a magnet that will stick together. Same thing here, that's going to hold those together. So these tend to be pretty strong bonds when they're dry. However, when you put them in water, they will usually break apart in there. So they will have a tendency to dissolve in water, anything that is bound ionically like that. So then we have some other weak chemical bonds. The hydrogen bonds in there that we talked about on water, those are a weaker bond in there. So creating that surface tension, the bubble on water. The other thing that you'll see sometimes is bugs walking on water. And it's not that bugs are all of a sudden holy and can walk on water. It's that the hydrogen bonds in there form a stronger bond than the weight of the bug to go down through the water. Now, if you go and try and walk on water, you're heavier. The force of gravity is pulling you down is stronger than those bonds. So you're going to sink, but the bug gets to walk on water. So water is not the only thing that can do the hydrogen bonds. You can have it here with ammonia as well. So when we have proteins folded up in the body, you can have hydrogen bonds forming in between them. Another type of weak bond is the van der Waals interactions. So when you have all these electrons around something, they're moving around all the time, but they're not always going to be symmetrically distributed. Some of them are going to move faster than others, and they may end up all clustered in one area in there. And it's just very temporary that they're clustered in one area, but that can allow it to have this temporary little charge in there. And that can allow it to bond to other things. So like with lizards, they can walk on walls. Spiders can walk on walls. So you've probably had the experience where you wake up in the morning and you look and there is the 8-legged little beast above your bed in there, and you're like, how are you sticking there? And I don't know about you, I don't like them, so I always picture that all of a sudden it's going to release and down he's going to come and attack me in the bed. They are not using little suction cups to stay on things. They actually have lots of little fine hairs in there that create these van der Waals interactions that hold them and stick them to the wall. So it isn't that they just turn off the suction cups and down they fall in there. Where it creates kind of some static in there and there's positive and negative charges. It's positive and negative charges, but they're really, really small. So you can go against the wall and you're not climbing up. Even if you grew hair on your palms and feet, you're not climbing on the wall. They're very small. So the molecular shapes in here, when you have these number of bonds, you're always going to get a predictable electrical or a predictable atom shape in here. I'm not too worried about you learning this part in here for that. Just know that it is a predictable shape in there and that it's going to make your molecules three-dimensional in there. And them being three-dimensional is important in biology because a lot of times the way they're going to interact with things is more like a lock and key mechanism in there. It's not that you're going to have little minuscule chemical reactions going on that you're changing things. It's they're either going to bond together or not, but they're not going to bond if they don't fit in the hole. So an example would be morphine, which is going to be very similar in shape in the key bonding area to the endorphin. So if you look at this area here on the box on the endorphin and on morphine, they look really similar. So in your brain, you've got receptors for the endorphins. And this is showing the endorphin bonding in the receptor, but the morphine can also bond in the receptor in there. And that's the mechanism that a lot of drugs are going to use, is they will fit into a receptor for something that's naturally occurring in the body. So if you make an artificial substance that can fit in that receptor, a lot of times you can trigger the same response, or you can go in there and you can put something in there that just stays there and does nothing. You can block that response in the body. Yes? Right. It doesn't take away whatever's causing the pain. It's just blocking your brain's ability to feel it. So that's why with narcotics, they are very effective for pain. They're the most effective thing we have. However, we tend to like the feeling of endorphins because it doesn't just do pain. It also makes you feel pretty good in there. So that makes them very addictive because as humans we go, it feels pretty good, I like it, give me some more. And some people are more prone to that where, you know, if you're the kind of person that you walk by the box of cookies and you go, one was good, the whole box tastes even better, those are more addictive nature traits where some people, they go, yeah, one was good and I'm moving on. Those people tend to have less of those traits in there. And it's not that you're good or bad for that because it can be a strength in other places in life, but it's just that is how you are chemically built.
So when things like narcotics and stuff like that don't work for people, does that have something to do with the molecular shape of things? Or
you can build a tolerance to these very easily. So what will happen is if you start to fill all of those receptors in there, you'll make more. And then you have a lot of them that are empty. So your body, it will take more and more and more to have the same effect in there.
The key problem is still there.
Yeah.
The fundamental problem is still there, so your body's still like, hey.
Right. Yeah. There isn't really anything you can do to fix that in there. If the person has a tendency, a lot of times people don't realize that they go, well, you know, it's not going to hurt. I'm just going to take a little more today. And people don't, you know, most people when they become addicted to things, they don't go at it and say, you know what, I think I want to be a narcotics addict. I'm going to take lots of these. It happens accidentally for them, where some people, their body will adapt to it even faster than others in there. Some are more prone to it than others in there. Some drugs it doesn't seem to do that. Some it does it very easily. And narcotics are one that it does it very easily.
So when you make more receptors, like for heroin addicts, they make more receptors, right? So that they can keep getting levels. The receptors never go away, right? So
it will change over time without it, but that withdrawal period in there, when they don't have the heroin in there, is miserable for them. Yeah. So if you're around somebody that's going through withdrawals like that and they're miserable, they're not making it up that they're miserable. They really are. And you're looking and you're like, how can you possibly really be in pain? Come on. You just want your drugs. Well, yes, they want their drugs, but they're in pain because they have distorted the system so much in their body that they really are uncomfortable in there. Yeah. And a lot of times when a person is on narcotics long term, it's really difficult. The longer they're on narcotics, there's a definite correlation about there's going to be less likelihood that they'll get back to normal in there. And it's not their fault. It's the way the body reacts to the drugs. Well, I mean, it's, you know, we all make bad choices, but there's a lot of people that accidentally become addicted as a result of an injury in there. And they don't know, somebody's not responsible in prescribing the medications, in monitoring them with them, educating the person in there. A lot of times people get busy and they're like, okay, yeah, you're injured. Here, take this for your pain. Come back in a couple weeks. And the person looks at it, and everybody's heard of OxyContin, but there's all kinds of generics that are very similar to that. They don't realize they're on something that is going to act just like it in there. So, there was the whole thing with Rush Limbaugh where he didn't realize he was getting into that. Kind of find it hard to believe that that man wasn't educated enough to realize what he was doing. But, I've seen lots of people that will, due to an injury at work, and it's just, here, take this pill and go away, that end up being somewhat addicted in there. And because their pain thresholds are so thrown off, it's very hard to get them back to a normal life. Did you have a question? Okay.
So, like, every now and then you overdose people, you can become non-responsive to morphine.
So what it does is it blocks it in the receptor so that it can't act in there. So if you... Yeah. Because what the endorphins, the morphine, and those drugs do is they slow everything down. So their respiratory rate will go way down. If you look at somebody who's on end-of-life care, they start breathing really shallow and everything, and people go, well, we just, the morphine killed them in there. And, kind of, but, it also kept them from suffering They were going to die anyway. A lot of people, I have family members that will look when somebody's died, don't give them morphine, I don't want them addicted. They're going to be dead in 2 weeks regardless. So, yeah. But it will do that. And so when they overdose somebody or when somebody overdoses themselves, so if the paramedics go out and they find somebody who's OD'd on something, they use the Narcan in there to block it. And, you know, in the hospital where it's like that and save somebody's life, they're usually not mad. However, if you do that to an addict, they're usually really mad in there. They're like, you ruined my high. Because I've known people that were with the fire department and they're like, oh God, here's another one. That they know as soon as they do that, that person is going to come to and be irate in there. Yeah. So when we look at the chemical reactions, usually they're written out with an arrow in here. So on the left side of the arrow, you're going to have the reactants, what you start out with. And you're going to have your products on the finishing side. And when you look at that, you're going to have these coefficients that are going to give you the relative amounts of things. So if you think of these kind of like if you're making some cookies. So you're going to have flour, sugar, butter, and let's put some chocolate chips in there. And what you get at the other end, cookies in there. So your coefficients are going to give you the relative amounts. So let's say that means you're going to have 1 cup of butter, 2 cups of sugar. Let's make them really chocolatey. 3 cups of chocolate chips, 2 cups of flour in there. So when you go to look at a chemical reaction in there, you're going to see these numbers here in front, where my leash is going to cut me off. Now I know how the dog feels. So you've got 6 carbon dioxides, 6 waters. They're going to react to give you 1 sugar, which is the C6H12O6, and 6 oxygens. So it's just so you can tell the relative amounts of things in there. That's what those coefficients are for in there. Does that make sense why we put those numbers there? So if you wanted to double that reaction in there, you don't just say, well, I'm going to put in 4 cups of flour and make twice as many cookies. Those aren't going to be cookies anymore. Those are going to be little bricks. You have to double everything in it. So when we look at chemical equilibrium, a lot of times the reactions are reversible. Cookies are not going to be reversible in there. Even if they were, I would throw off the equilibrium by I start taking from this end of them so it never has a chance to build up. But with the equilibrium, it's kind of like being on a teeter-totter in there. If you put too much, if you put more reactants in there, it's going to tend to want to make more products. If you start building up products, it will tend to want to shift and slow things down in there. So the speed of a reaction a lot of times is going to be influenced by how much of stuff you have. And the equilibrium is just where you have that balanced ratio, which is different for every reaction and under different circumstances. So when we look at water in here, water is going to support life forms in there. Water is going to be what most of our world is made up of. It's a little unique that it exists as a liquid, gas, and a solid on Earth. It's going to participate in your reactions to sustain life. So water is a polar molecule that we talked about this a few minutes ago in here, where it's able to do these hydrogen bonds in there. And because of being able to do those hydrogen bonds, it's going to give it some properties. It's going to have this cohesion. That's what allows it to make that bubble on top of a glass. If you spill water, it's also going to kind of stick together in clumps on the table. It doesn't shatter and go everywhere. You'll have the puddles made in there. That's going to help it to move against gravity in plants because it's going to be able to stick to things. So it also has the ability to adhere. It's got adhesion in there where it can cling to other surfaces. If you fill a glass of water and you turn it over and you set it down, is it dry? No, there's still water left on the inside. And that's because it will adhere to surfaces too. So it gives that surface tension in there, that bubble across the top. Water helps to moderate temperatures a lot. So it can form a heat bank in there where it can absorb and release a large amount of energy with only a little bit of change in its own temperature. So in western Washington here, we've got the Puget Sound that acts as a giant heat bank. Versus over in eastern Washington, on the other side of the mountains, they don't have the influence of the Puget Sound. So in eastern Washington in the winter, if you haven't been there, it's much colder than it is here. In the summer, it tends to be much warmer than it is here. So their temperatures will fluctuate a whole lot more than ours here because the water keeps us from getting too warm or too cold in there. So the water molecules, the faster they move, the more kinetic energy they have. And we can measure that in substances by looking at the heat. Heat is a form of energy, and it measures the matter's total kinetic energy due to movement of the molecules. So it will be partially dependent on volume. And some of these here with heat and temperature in there may be kind of hard to wrap your head around in there. When you think about, you go, why is volume going to have anything to do with that? Volume is how much space you have to run around in there. So if you put something in a pressure cooker, it's going to cook faster because you can heat it up more because it's all contained in there. You put the pressure to contain it. So temperature is a measure of heat intensity. It's the average kinetic energy regardless of the volume in there. Heat will move from warm to cool in there. It's the heat energy that moves, not the cold. So when you put ice in a glass of water, what happens is it's not the ice cooling off the substance in or the water that's in there. What happens is the heat from the water goes into the ice and melts it in there. Likewise, if you open the door to your house and it's warm inside, cold outside, you're not letting the cold air in, you're letting the heat out in there. So when we measure heat, we use calorie as the unit of measure in there, or the unit of heat. It's how much heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. The kilocalorie is going to do 1 kilogram of water by 1 degree Celsius. So when you look on food labels, what you're actually seeing is kilograms or kilocalories on there of energy in there, not calories. And I think the main reason they do that is when you say the metric system in the United States, you put anything in the metric system and it will freak out half the population. So we just call it calories on there. If you buy food in another country, they don't indicate how many calories there are on the package. It's kind of nice if you look at things and you go, oh, I'm not going to eat that, it's got too many calories. You go to another country and then they're going to have it in joules. And you look at that and it's like not something you can relate to, and you're like, no guilt in eating that, looks good, here we go. I always think those Canadian candy bars are healthier for me because of that. So the joule and the kilocalorie, there's the units for these. It's one of those things that if you have to do the calculations, you remember the units in there. I'm not going to have you calculating out no math stuff on this. Knowing the definition that it's like a unit of heat, but I'm not going to ask you like, oh, 1 joule is this many calories or something like that. I'm really not big on doing math unnecessarily.
So calories and joules, you know both?
You would want to know both. We're going to go through and give you some list of stuff to study before you leave today too. to get you started. Yeah. So the specific heat, yeah, I'll post things like that. When I send out notices in there, that's, I might be lonely sometimes, but I don't do that to look for friends. So. Anybody out there? So specific heat, this can be kind of an abstract idea as well. It's the ability to stabilize the temperature. And so it's kind of how fast does something heat up in there. So when you you look at how fast does water heat up. Water is really resistant to being heated up. It takes a lot of energy to boil water in there. So the specific heat of water they use as kind of a reference for things, is considered 1 calorie per gram per degree Celsius in there. Ethanol, if you wanted to boil ethanol, it's going to heat up a lot faster in there. It's only 0.6 calories per gram per degree Celsius. So what that is saying is that it's going to take 1 calorie to move water a certain distance. It's only going to take 0.6 to move ethanol the same distance in there. And then your specific heat of water is 10 times that of iron. So if you had 1 for calorie per gram for water, that would mean iron would be at 0.1 in there. So if you put a pot on the oven and you look and you go, maybe you've done this and you're like, okay, you're trying to boil some water and you're looking at it and you're like, okay, how close is it? It's been a while, it's not boiling. You stick your finger in it to test it. Then you accidentally hit the pan that it's in. That pan is way hotter than the water. So that pan heats up long before that water does in there because that water has a higher specific heat.
Is it true that it takes longer for water to boil at a higher elevation?
Yeah, the elevation will have an effect on that because you have different atmospheric pressure on the water in there. I mean, it's one of those things. If you're out, if you live at a higher elevation in there, they'll usually put differences on your cooking instructions. If you're out hiking and you're like, okay, I'm going to boil something with my camp stove, it always feels like it takes a long time for your camp stove to build. It's just the way it is. If it starts at a colder temperature, it's going to take longer to warm it up. So the colder you start with, the longer it takes to get there. So if you take hot water out of the tap to boil, it will go faster. However, then you got to look and you go, that whole time it's running my hot water heater, which has a bigger effect on your power bill. I don't know. It's more about what's going to be more for your convenience at that point. So evaporative cooling, what happens when you boil water is the kinetic energy of those molecules are moving and moving and moving really fast. And eventually some of them get so fast that they just spin their way off and leave. And when they leave, they take their energy with them, which is going to reflect a change in heat in what's left behind because there's less energy left behind. So when you sweat, what's happening is as it takes off, takes some of its energy with it, leaves you a little bit cooler behind in there. So that's the evaporative cooling. So the heat of vaporization is how much heat a liquid has to absorb for 1 gram of it to be converted from a liquid to a gas. In there, again, you look and you're like, how many ways can we talk about boiling water in here? And so to evaporate 1 gram of water at 25 degrees Celsius, it needs 580 calories of heat in there. Water will insulate things. So it will insulate, if you look at a frozen lake, you're going to actually have it be somewhat insulated underneath when there's the layer of ice on the top. The ice is going to float though, because most things as the temperature decreases, they get more dense. But water does that till it gets to about 4 degrees Celsius. Then it's at its densest, and it starts to make the crystal structure in there, and it expands a little bit. So that's why the ice cubes are going to float on the water underneath it that is going to be closer to 0 degrees Celsius in there, as it's expanded a little bit once it's frozen. We will in just a second in there.
I just know, I don't want to miss anything, and I just want to go back to my fall. I don't want to stop or anything like that.
We will once before we get to the pH in there. So we'll go through this one little last section in here, and then we'll take a break. So water acts as a solvent in there, so it allows things to dissolve. A solution is going to be a liquid that's got a completely homogeneous mix of 2 or more substances in it. So your solvent is going to be the dissolving agent or the liquid. The solute is the solid stuff that's going to dissolve in there. And we call it an aqueous solution if you have water that is going to be the solvent. So one of the things that it will do is it creates this hydration shell around the molecules that go into it. So you can kind of look at it and say, okay, when you've got sodium and chloride together, positive and negative charges, when they're alone and dry, that bond is really strong. There's nothing else around for them to bond to. However, when you put them in the pool of temptation where there is all kinds of other things to bond to, they start to look at their partner and they go, I don't know, maybe I might want to bond to one of these. And then they get a little greedy about it, and the sodium's kind of looking at it going, I could have 1 partner, or I could have 5 partners around me in there. So that's when they will choose the 5 partners. Well, then we've got the female over here, and she's got like, what is it on this one, 7? So, yeah, she's not much better in there. However, after a while, all these partners are taken up, so when you continue to put more sodium chloride in there, it's not going to dissolve. It will become saturated. Everybody's going to go get the multiple partner thing that can, and when you're too late in the game, you're stuck with your first partner in there. So something that is hydrophilic has an affinity for water. It likes water. Hydrophobic, it doesn't like water in there. It repels it. So if you've got a phobia of something, you don't like it in there. The only example we have really where we use philic in everyday language is pedophile, and I hate having to use this as an example. They really like kids in there.
And you said the hydrophilic is the one that likes water?
Yes, in there. So then the colloid, these aren't real common, but it's a stable suspension of fine particles in liquid. If you see one, it's kind of like seeing an eternal snow globe, where the flakes never are going to settle to the bottom. It's always going to be in snow globe format with them floating around in there. And that's what a colloid looks like. The eternal snow globe, it never settles in there. It will never make the pile at the bottom in there.
So like when we have a cleaning solution, we'll make like, I don't know, 1% water and like a little bit so much bleach.
Mm-hmm.
Is that considered a cold really?
No, because the bleach is going to be completely dissolved in there. It's hydrophilic and hydrophobic don't really apply to using solutions. It's just more substances that like water. Oil would be hydrophobic, so it's not going to mix in the water. So you could probably say the other things are hydrophilic. They're friendly and they get along with it. So we'll go ahead and we'll take a break for a few minutes here. If you want to see your here. So when we look at solute concentrations, basically what that is doing is looking at how much solid we put in that liquid. And the reason that this is important is if you have to distribute a medication to a person through a liquid, say like in an IV, you're going to get to calculate this till the cows come home in a math class in here. And so the good news is I don't have to put you through those calculations in here, but just a little bit of what's behind these calculations is for those of you that are not in that math class yet. So the molecular mass of something is basically the sum of all the masses that are in a molecule. And it's going to tell you how much of something there is. One molecule, if we measure one atom in there, that's really small. It's not like if you're making an IV, you're going to say, get 6 atoms of this and 7 atoms of that to put in there. We can't see 6 or 7 atoms in there, and we're bigger than that. We need more than that. So what we use is the mole in there. And what the mole represents is 6.02 times 10 to the 23rd units of something. So that's basically saying 6 with 23 zeros after it. So instead of saying you need however many this number comes out to be atoms of this, we say get a mole of it. So it's a lot like saying a dozen. If I say go grab a dozen eggs, you know that that carton's a dozen eggs in there. You go get a dozen buns at the bakery. You go buy a dozen hot dogs or something like that. That dozen is a unit we use. Is just a short way of saying go get 12. So when we say go get a mole of something, in there you can do that. And the mole is real convenient because on the periodic table, that number that is the mass of one atom is also the mass of 1 mole in grams. So then you don't have to calculate that out. It's just that number is there for you. A mole is 6.02 times 10 to the 23rd units of something. That is a number you will want to know. When you go into chemistry, I mean, I hadn't used that calculation for like 15 years, and the number came back to me like that because I'd done so many calculations with it. You just know that a mole is 6.02 times 10 to the 23rd, and the guy who found it, his name was Avogadro, so they call it Avogadro's number. I'm sorry, what was that? So it's, you could have a mole meaning this many atoms in there, a mole of atoms. If there was that many people in here, we could say we have a mole of people. It's like when you say dozen, dozen doesn't always mean eggs. Dozen means 12 of anything in there. So a mole of something is that many of anything. What, you haven't taken chemistry yet then. Yeah. Yeah. Mole is the chemistry behind it in there, the name that's behind it. So when you're calculating the molarity of something, what you're looking at, and molarity is abbreviated as a capital M, is how many moles of something you have in a liter. So if you need to make a certain molar solution, then you're going to need to know, well, okay, how many grams are in 1 mole of this to make a 1 molar solution in there. So again in here, molarity, know this, that it's basically how many moles of the solute are in the solution. Mole is this number. You don't have to do the calculation in here. More likely to be matching. I have to get your test graded in a certain amount of time, so the number of fill in the blanks is limited because they take longer to grade. You're going to see more multiple choice and matching in there. The multiple choice and matching is more what you're going to see on a standardized test. However, fill in the blank is a lot of what you'll see in 241 and 242 on a lab test. So that's why you get a mix. Is I don't teach that, no. But I do, as the instructors, we see each other's tests. So that's why I look at it and say, okay, I know where you're going afterwards. I want you to be successful in where you're going afterwards in there. So that's why I've changed it and put more of those in my tests than I used to. So when we look at acids and bases in there, in living organisms in there, this is looking at the pH of things. When you have water and you want to split it in half, if you look at water, it doesn't split in half. There's no way of cutting that in half equally in there. So what you're going to have to do is the oxygen is going to have to go with one or the other hydrogen. Remember, this represents that these two are sharing electrons. So we'll say it picks this one to go with. Now when you go to break up this relationship, you've got this big team here. Remember, oxygen's still more electronegative in there. And they say these are the shared electrons between us. So it's not going to be an amicable divorce in there. Hydrogen's going to be the one that says, you know what, I'm just walking away with nothing. So the hydrogen leaves its electron behind and has a positive charge. This is going to gain an extra electron. So it will have a negative charge between the two of them in there. So this is the hydrogen ion, this is the hydroxide. This doesn't really like to float around by itself a lot, even though we still talk about it being this way. In reality, it's going to become the hydronium in there, where it just hooked to a water. It's going to join on to another couple and be the third leg in there, although technically it's still single. So when we look at the reactions between having it be in this state and being as water, it's a reversible reaction in there. So it can go back and forth between the two. In pure water, what it means is that you're going to have one molecule in every 554 million dissociated. So we make that into an exponent in there, and so it becomes 1 into the negative 7th molarity of it is dissociated. Thank you. So it's very little of it is dissociated in there. And when that's going to mean we have a pH of 7. So when we look at that concentration of how much of it is dissociated in there, we take the negative log of it. The nice thing about this little negative log equation is for what you need for pH, you don't have to do any math of it. There is math behind where it came from, but you look and you go, oh, negative 7, 10 to the negative 7th molarity. pH of 7. You just look at the number, ignore the negative sign in there. So with the pH scale, it's going to go from 0 to 14. In the middle, you have 7. This is where water is. It's neutral. Over here, you have basic. You have the hydroxides. Over here, you have more free hydrogen ion. And it's acidic. We tend to get this idea that acids are bad, and I think it comes from the idea that when you're a little kid, you know, you're told don't touch the batteries that leak on there. You don't want that battery acid on your hand. You're told that so emphatically that you think that if you touch a battery that's got battery acid, that your hand is going to immediately burn off. Then at some point you grow up, you move out, and you have a battery that leaks on something. Mom's not there to clean it up for you. So you have to clean up the battery and you touch it and you're like, hand's still there, not burned off. Mom lied in there. And so acids and bases, it's not good or bad in there. It's having it in the right place in the body is where you need to have things. So, you know, we look battery acid around pH 1, so are lemons. Nobody really views a lemon as a bad or a harmful thing. Now, you don't want battery acid on the paint on your car, just like you don't want to put a lemon on your car. If you cut open a lemon and stick it on your car, you're going to ruin the paint. But it takes time in there. Your gastric juice is about a pH 2 in your stomach. That's very acidic. You vomit on your car, you're going to do some damage to it if you don't wash it off on there. Coca-Cola, between pH 2 and 3. Nobody really hesitates to put that down their throat in there. So acids, it just depends where they are and which acids it is in there. However, if you had something of a pH 2 coming out where your urine is, that's not going to feel good at all in there. So the proper pH in the right place is what is important in there. Something that is a strong acid can be harmful to substances. It's going to be more likely to react with substances. Just like at the other end of the spectrum, something that's a strong base is going to be reactive with some substances. Because it is a logarithmic scale in there, what that means is each time you change a whole number, it's actually a tenfold difference. So if you go from a pH 8 to a pH 9, 9 is 10 times more basic than the 8 was. 8 is 10 times more basic than the 7 was. So it increases the difference between a 9 and 10. 10 is 10 times more basic than the 9 was in there. So as you move out, the difference is bigger and bigger. Same thing going down this way. A pH of 4 is 10 times more basic or more acidic than a pH of 5. pH of 3 is 10 times more acidic than a pH of 4.
The more you go that way, it's more acidic.
Yep, so more acidic, more basic. Yes. So the acids and bases in there, we can have weak or strong acids or bases. With a strong acid or base, whatever you put in here that's going to create all of these free hydrogens is going to completely dissociate. It's a one-way arrow. If it's a weak acid, some of it dissociates, not all of it does. Same thing with a strong base. Completely dissociates is strong, partway is weak. Can what? Dissociate? I didn't hear the whole.
What does dissociate mean?
Dissociate means comes apart.
Comes apart. Okay,
Yeah.
sorry. Or is it kind of like dissolve?
Kind of like dissolve.
Okay. I was just trying to understand.
Dissociate's the word they use with acids and bases, even though it's usually dissolving in there. So when you look at an acid, there's more than one way that they dissolve acids, but usually they say it's going to donate additional hydrogen ions. With the base, they'll look at it and say it either accepts hydrogen ions or creates hydroxides in there. So the definitions for it depends on, there's multiple definitions that are given for it in there. In here, if you think acid, the lower number going this way, base, the higher number going this way.
Are you going to use like the H plus, the OH minus, or are you going to put that on the test, or are you going to use
These are very common abbreviations you'll want to get. Yeah. Yes. So with the pH scale, if you are a person that needs to do the math to accept something, it's here. If you can say, oh yeah, somebody did the math for something there, and I can be okay with that, basically what the pH scale says is, okay, you take the negative log of something, and it's going to give you the pH. So a negative log of a negative 7, or 10 to the negative 7, is going to give you the 7 on there. So it's negative times negative gives you a positive in there. That's where the math comes from for the pH scale in there. So if you change the concentration of the amount of hydrogen ion or hydroxide ion, that's going to change that number for the log in there. So a buffer is going to be a substance that helps to slow or minimize the pH change in a solution. So a lot of times in the body, you're going to have a lot of buffers because pH is going to control when processes will happen. So when you eat some food, yes, you've got acid in the stomach, but you're going to put in something in your stomach that is not as acid as the environment is. And it's going to sit there in the acid and get ground up and have enzymes come into it. And the way it's going to know it's time to move on to the next step is the pH needs to get acidic enough that it will trigger that sphincter muscle at the end of your stomach to open up and say, okay, it's done, send it to the next end in there. So pHs turn things on and off a lot of times in the body. Whether or not you inhale or exhale is controlled by a pH in there. If you're holding your breath in there, what's going to happen is you're building up a pH change, and you're going to have more and more of a drive to exhale it in there to try and balance out that. So the buffers just make it so that we're not overly sensitive on those things. It will help to absorb the pH change in there. Other things where the pH of stuff comes into play in the environment, acid precipitation in there. So it's considered anything that comes down out of the sky with a pH less than 5.2 in there. A lot of the stuff that you put out there that is pollution, when it interacts with water, it will create an acid. If it interacts with water that's in the frozen form, you have acid snow. If it interacts with water that's a vapor, you've got acid fog in there. So it's not just acid rain that we will get in there. And then when we have the pH changes that will go in carbon dioxide in the ocean in there, it will form carbonic acid in there, and it will affect the coral and other organisms. So the pH changes there. Where we've studied this a lot is volcanoes create a lot of this type of change in the ocean, and you'll see that the coral, when there is these volcanic vents in there, downstream from there will be greatly affected by it. So we're going to stop with the notes there.